Welcome to EDU World Space.
Hey guys, so in this problem, we're given that rho is the density of our liquid, omega is the angular velocity, and r is the distance from the vertical axis. The first thing that's always good to do in any physics problem is to draw a couple diagrams. And as you can see, I've done that here already, a side cross-section view and a top view. As you can notice, there's this little tiny box here, which represents a tiny area or a tiny part of the water with dr. Okay, so let's do real quick some, let's start by doing some force analysis on this box. Okay, so if you can imagine this as a particle rotating around in the cylinder, you know that there's got to be a centrifugal force pushing the pushing this particle outwards towards the wall, and we're going to call this Fc, which is a centrifugal force. That force acting along the left area of this box is going to be called P. Rather, the pressure is going to be called P. Okay, so now what we also know is that on the right side that there's going to be another force pushing inwards, so we'll call that F F in. Okay, and the pressure here is also going to be P, same pressure, but we also have to account for any changes in pressure that might have occurred over this tiny little area or this tiny little distance dr. So what we can do is take our change, our, let's see, a little expression for the change in pressure, which is change in pressure with respect to r, and multiply it by that tiny distance dr. Okay, so now that we have that, let's see, what else do we know? Well, based on our knowledge of angular acceleration, we know that the acceleration towards the center of this part, towards the center of the cylinder acting on this particle is going to be equal to, hold on, a, let me move that up a little bit. A is going to be equal to r omega squared. Okay. Now, what we can do, given this little net force diagram we have going on here, and our angular acceleration, sorry, our linear acceleration, is we can try plugging that into Newton's second law of motion and see what we get. So for our forces, our net forces, we're going to have F in, which is P plus change in pressure over dr times dr minus P. Okay. Now you might be saying to yourself, well, this is not a force. And you'd be right. A force has to, a pressure, what we can use, or what we can do rather, is multiply this pressure by the areas here on either side, which we're going to call dA. And since we know that, oof, since we know that area times pressure gives us a force, which is exactly what we're going on, exactly what we got going on here, we know that we have our net force. Okay, we're going to equate that to the right side, but you're going to notice here that we need a mass. Okay, well, what we have, what we have is rho, which is our density of the liquid. And in order to get a mass from that, we need to multiply that by a volume. Okay, so let's start by, oh, let me try to make that more distinct. Here's rho, okay? And we need to multiply that by a volume. Okay, so what would the volume of this little box be? Well, let's see. we know that its width is going to be dr, and we can get an area, which we use on this side also, dA. Okay, so now we have our expression for mass, and now all we need to do is plug in acceleration, which is r omega squared. All right, so simplifying this whole equation, what we're left with is, let's see, change in pressure is equal to, let's see, let me make that a little bit better, equal to rho, which is our density, times r omega squared. Okay, now what we want to do is to find an expression for pressure, what we got to do is integrate both sides, right? And the way we're going to do that is on this side. Let's draw that in right now. We're going to be integrating from our initial pressure, which based on the problem, we know is going to be P0, okay, to some to our final pressure at distance r, which is going to be P. Okay, and now we look at the right side. Let's draw in the integration, and we're going to be going from, let's just say, some reference point where the radius is 0. That would be at the center, going from 0 to whatever radius we're looking for, r. And we also need, real quick, write the dr right there, just so that we know we're integrating with respect to the variable r. Okay, so carrying that out, on the left side, we're going to get final pressure P minus P0, so the initial pressure at the inside right there, and that's going to be equal to, well, side, all we really have to look at, these are just constants. Oh, that is rho is a constant and omega squared is a constant. So imagine they're not there. Integrate the r, and what we're going to get is 1 half rho, let's see, rho omega squared r squared. Okay, and that's just some basic integration. Okay, now we're almost done. The very last thing we have to do, and remember that the problem was asking for a formula for pressure, and we got that real easy. All we have to do is move the initial pressure over to the other side of the equation. And what we get is pressure at some distance r is equal to the pressure 0 plus 1 over 2 rho omega squared r squared. Okay, and that's all.